Every linear system AX equals B you will ever encounter, whether it has two equations or 200 equations, falls into one of exactly 4 categories. And I can tell you which category just by knowing a single number, not the size of the matrix, not the entries, just the rank. There are 4 doors, 4 possible outcomes, exactly one solution for every B, 0 or one solution, infinitely many solutions for every B, or 0 or infinitely many solutions. To see why, let's start with what the rank controls. Rank R equals the number of pivots after row reduction. It's the count of truly independent equations in your system, right? 2 constraints always hold. R is at most m, the number of rows, and R is at most n, the number of columns, right? This makes sense because you can never have more pivots than you have rows, and you can never have more pivots than you have columns. Now, here's the key insight. Rank creates 2 gaps. Right? The first gap is n minus r. That's the number of non-pivot columns, which become free variables, variables that can take any value. This gap controls uniqueness. Right? So if n minus r is greater than 0, you have free variables, meaning solutions are not unique. The second gap is m minus r. That's the number of 0 rows in the reduced form. Each 0 row imposes a condition that B must satisfy, violate it, and the system has no solution. This gap controls existence. So we have 2 gaps, 2 independent levers, and together they determine which of the 4 solution cases we're in. Start with the cleanest case. R equals M equals N. A square matrix with full rank. Take A equals the 3 by 3 matrix with rows 1, 2, 1, 3, 8, 1, and 0, 4, 1. Row reduce this matrix and R equals the 3 by 3 identity. 3 pivots, 3 rows, 3 columns. Now let's compute the 2 key gaps. First gap, n minus r equals 3 minus 3 equals 0, meaning no free variables. Second gap, n minus r equals 3 minus 3 equals 0, meaning no conditions on B. Every B is solvable and the solution is always unique. For example, if B equals the vector 2, 12, 2, the unique solution is x equals 2, 1, negative 2. Right? You can check 1 times 2 plus 2 times 1 plus 1 times negative 2 gives 2. 3 times 2 plus 8 times 1 plus 1 times negative 2 gives 12. 0 times 2 plus 4 times 1 plus 1 times negative 2 gives 2. And this is the invertible case. X equals A inverse times B. There is exactly one solution for every B. Now let's make the matrix tall and thin. More rows than columns. Take A as a 4 by 2 matrix with rows 1, 3, 2, 1, 6, 1, and 5, 7. This matrix has rank 2. After elimination, R equals the 2 by 2 identity on top, 1, 0, 0, 1, with 2 rows of zeros below. Let's check the gaps. M minus R equals 2 minus 2 equals 0. That means no free variables, so any solution that exists must be unique. But m minus r equals 4 minus 2 equals 2. Those 2 0 rows impose 2 conditions on B. Consider the left panel. For B equals 4, 3, 7, 12, those conditions are satisfied. You can verify 1 times 1 plus 3 times 1 equals 4. 2 times 1 plus 1 times 1 equals 3. 6 times 1 plus 1 times 1 equals 7. And 5 times 1 plus 7 times 1 equals 12. The 0 rows produce 0 equals 0. No contradiction. So the unique solution is x equals 1, 1. Now consider the right panel. For B equals 1, 1, 1, 1, a 0 row in R produces 0 on the left side, but a non-zero value on the right, and that's a contradiction, so there is no solution. This is the 0 or 1 case. When the matrix is tall and thin with full column rank, you either get exactly one solution or no solution at all. Now flip it, short and wide with more columns than rows. Take a 2 by 4 matrix A with rows 1, 1, 2, 2, and 1, 2, 6, 3. This has rank 2. the reduced row echelon form R equals 1, 0, negative 2, 1 in the first row, and 0, 1, 4, 1 in the second row. Notice there are no 0 rows. M minus R equals 2 minus 2 equals 0. That means every B is solvable. And there are no conditions on B. But n minus R equals 4 minus 2 equals 2 free variables. All right, so there will always be extra degrees of freedom. Columns 1 and 2 are pivot columns, while columns 3 and 4 are free columns. For B equals 1, 1. The general solution is x equals 1, 0, 0, 0, plus s times 2, negative 4, 1, 0, plus t times negative 1, negative 1, 0, 1. We have two free parameters, s and t, giving infinitely many solutions. The key takeaway for this case, the system is always solvable, but never unique. 3 cases down, the fourth and final case is the most complex. Both gaps are non-zero. Take A with rows 1, 2, 2, 4, 3, 8, 6, 16, and 4, 10, 8, 20. This is a 3 by 4 matrix, so m equals 3 and n equals 4. After elimination, R equals 1, 0, 2, 0, 0, 1, 0, 2, 0, 0, 0, 0. The rank is 2. Now both gaps are active. N minus R equals 4 minus 2 equals 2 free variables, and M minus R equals 3 minus 2 equals 1 condition on B. Let's try B equals 1, 3, 4. When we apply the same row operations to B, the 0 row gives 0 equals 0, and the condition is met, so the system is solvable. With two free variables, x3 and x4, we get infinitely many solutions. X equals 1, 0, 0, 0, plus x3 times negative 2, 0, 1, 0, plus x4 times 0, negative 2, 0, 1. Now change B to 1, 3, 5. This time, the 0 row gives 0 equals 1. A contradiction. There is no solution. Same matrix A, different B. The answer jumps from infinity to 0. It is never exactly 1. This is the hallmark of case 4. When both gaps are non-zero, you get either 0 or infinitely many solutions, but never a unique one. Here's a fact worth understanding. A linear system can never have exactly 2 or exactly 3 solutions. Let me show you why. Suppose P and Q are both solutions to AX equals B. That means AP equals B and AQ equals B. Now consider the vector P minus Q. By linearity, A times the quantity P minus Q equals AP minus AQ, which equals B minus B, which equals 0. So the difference P minus Q lies in the null space of A, the set of all solutions to AX equals 0. Now here's the key insight. The null space is a subspace, and subspaces are closed under scalar multiplication. This means if the null space contains any non-zero vector V, it must also contain 2V, 3V, negative V, 1/2 V. In fact, every real scalar, multiple C times V, that's infinitely many vectors in the null space. But how does this give infinitely many solutions to the original system? Well, if V is in the null space, then P plus CV is a solution to AX equals B for every real number C, because A times P plus CV equals AP plus C times AV, which equals B plus 0, which equals B. So two distinct solutions immediately give infinitely many solutions. The only alternative is that the null space contains only the 0 vector, which means P must equal Q. In other words, there is exactly one solution. And therefore, for any linear system, the number of solutions is always 0, 1, or infinity. Right? No other count is possible. Right? As a small contrast, note that a nonlinear equation like x squared equals 1 can have exactly 2 solutions, but that can never happen for a linear system. Now let's pull back and see the whole picture. We'll draw a 2 by 2 grid that classifies every possible linear system. One axis asks, does R equal N? This is the uniqueness lever. When yes, N minus R equals 0, meaning no free variables. The other axis asks, does R equal M? This is the existence lever. When yes, m minus r equals 0, meaning no conditions on B. Let's fill in the 4 cells. Top left, r equals m equals n. There's exactly one solution for every B. This is the invertible case. Top right, r equals m, but r is less than n. There are infinitely many solutions for every B. Free variables give infinite choices, but existence is always guaranteed. Bottom left, r equals n, but r is less than m. There are 0 or 1 solutions. Uniqueness is guaranteed when a solution exists, but existence is not. Bottom right, r is less than both m and n. There are 0 or infinitely many solutions. Existence is not guaranteed, and if a solution does exist, free variables ensure infinitely many. 4 cells, 4 cases. This is the complete classification of all linear systems. Here is the full summary of all 4 cases. Case 1, r equals m equals n. The reduced form R is the identity matrix. There are 0 free variables, since m minus r is 0, and 0 conditions on B, since m minus r is 0. This gives exactly one solution for every B. Case 2, r equals n, which is less than m. The reduced form R has the identity on top with 0 rows below. There are still 0 free variables, so the solution is unique if it exists. But there are m minus r conditions that may fail, so you get 0 or 1 solution. Case 3, r equals m, which is less than n. The reduced form R has the identity alongside extra free columns. There are m minus r free variables, but 0 conditions on B. The system is always solvable, giving infinitely many solutions for every B. Case 4, R is less than both m and n. The reduced form R has both 0 rows and free columns. Both gaps are non-zero, n minus r free variables and m minus r conditions, right? You get either 0 or infinitely many solutions. The key takeaway, rank tells you the shape of the answer. The specific entries of A and B fill in the actual numbers. One number, the rank, 2 gaps, m minus r and m minus r. 4 cases. Every linear system falls into exactly one of these categories. Door 1, when r equals m equals n, there is exactly one solution for every right-hand side. Door 2, when r equals n but is less than m, there are 0 or 1 solutions. Door 3, when r equals m but is less than n, there are infinitely many solutions for every right-hand side. Door 4, when r is less than both m and n, there are either 0 or infinitely many solutions. The rank is the golden key. It opens the door. The rest is just arithmetic, one number, 2 gaps, 4 cases, every system.